Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection, as usual. Today I would like to talk about the so-called curse of dimensionality. So in some sense, well, I will pick out a certain theorem, but in some sense, it's a following, well, fact of life, whatever you want to call it. So our brain is kind of used to low dimensions, dimensions 2, dimensions 3 at best, sometimes dimensions 4. I will show you some examples in dimension 4. Um, and then the brain kind of makes this assumption that everything kind of stays fixed in higher dimensions. So this is this curse of dimensionality. But a lot of things are just flukes of low dimensions. So in high dimensions, really, really creepy things happen. So crazy, creepy mathematics happens. Counterintuitive up to a point where you can call it a paradoxon. It's not really paradoxical, so it's not really a contradiction to anything. It's more like really counterintuitive. As I said, I will pick out a certain theorem of this behavior, but it's kind of a general flavor. So our high dimensions are pretty creepy. And this is very surprising in some sense because, well, when you start off, you don't really know what higher dimensions are. And it took quite a while if you track back the history of mathematics, for people to accept that higher dimensions exists. Nowadays, you just learn it as some coordinates in some vector space or whatever, which kind of makes sense. But still, we kind of tend to underestimate, our brain tends to underestimate how creepy, how crazy high dimensions actually are. So the theorem I'd like to pick out for today is basically about volumes of spheres. We'll see. So let's get started. Um, so I would like to talk about hypercubes and hyperballs. So the definition of hypercubes and hyperballs, as I said, it's pretty straightforward. You take the definition you like from dimension 2 or 3, in this case even dimension 1, which is a little bit silly. I will come back to that in a second. But you take these definitions and you generalize them to higher dimensions, which is not so hard. So let's have a look. So the ball is this purple thing in the middle. The two-dimensional ball is a filled circle. The three-dimensional ball is more like what you call a ball. But mathematicians just call everything a ball. Whatever. So you might want to call the two-dimensional one a disk. But anyway, so let's just call them an n ball. So this is a 3 ball, this is a 2 ball, and the 1 ball is a little bit strange. It's just a line, a filled line, whatever. By definition, that's the 1 ball. And what is that? Well, these are just all points such that you know how the equation looks like, right? For the two-dimensional space, it would be all points with x squared plus y squared equals 1. And you just generalize that um, to as many coordinates as you want, like 500 coordinates, whatever. So the hyperballs, dimension 1, 2, 3. I will show you a hyperball of a dimension 4 in a second. But basically, that's the setup. You have hyperballs. You would like to think of it like the interior of a balloon, if you want. So the filling of the balloon. I'm not interested in the surface of the balloon. It's filling of the balloon. Really a ball, right? Something solid. And they tend to sit in a hypercube, in a 2 cube, in a 3 cube, in a 1 cube. 1 cube is again a bit silly. The 1 cube actually is the same as the 1 ball. Okay. So the 1 cube, I would like it to be with side lengths 2, and in this case, it's the same as the ball. So here in the picture, you have side lengths 2, and I would like to have side lengths 2 here the same, side lengths 2, such that I can perfectly fit my circle or my filled circle, my ball, into this 2 cube or into the 3 cube, so side lengths 2. And this, of course, works. It's pretty much clear because right, my hyperball here is in this case I normalized it to be of radius 1, so the radius is 1, and if the radius of the hyperball is 1, it fits perfectly into a box with side lengths 2. And I would like to make this clear. I really have in those pictures I have a ball which fits perfectly into a box. So you can't fit a bigger ball into the same box. So it's really the perfect fit into the box. And the box is also pretty easy to define. It's this definition, just all coordinates in this case that are just between -1 and 1. So as I said, in dimension 1, they're just the same, and then they're not the same anymore. So the hypercube, the 2 cube is here on the outside, and the 3 cube here is it's a box, right? So the interior of the box. Again, I would like to think of it like having an interior. So it's kind of filled. I want to measure its volume, but still I want to put a sphere inside as in the picture, or a ball inside as in the picture. And the question that comes up is here, so what is actually the ratio of the volumes? So how much space is filled in my box if I put a ball inside, right? I have a box, I put a perfectly fitting ball inside. How much space does my ball fill in the box? Good question. So as I said, so here are some low dimensional ratios. So in dimension one, ball equals cube. So well, ratio is one. Then it's about 0.79, and then it's about 0.52. So right now I'm kind of not really able to guess what will be going on here, and I'm interested in the limit, of course, n tends to infinity. So what happens with this ratio of volumes if n tends to infinity? Just from those low dimensional examples, I can't quite tell what's going on, right? I mean, it might that it approaches some whatever, some constant between one and it's certainly not bigger than one. It's certainly not smaller than zero. So maybe it approaches some constant between one and zero. But then you think about it a little bit, and you would like to draw the four-dimensional setup, which is a bit hard to draw. So let me try to explain my idea of how to draw the four-dimensional setup. I shouldn't have said my idea. That's certainly not my idea. That's a very well-known idea in low-dimensional topology. Links to everything are in the description, of course. In particular, I'm following a nice article about the theorem I'm going to talk about. I don't want to spoil it right now, which is also linked in the description. Anyway, so in order to think about higher dimensions, I would like to take the following approach. As I said, well known in low-dimensional topology. I would like to think of a movie. So actually, well, our world is not three-dimensional. It's actually secretly four-dimensional, and we all know that. So we're seeing a three-dimensional picture, but there's a movie going on in our heads. But the world is processing, right? It's progressing forward, or in this case not backward, but of course a movie you can play it backward anyway. Anyway, so there's another direction, and that's time. And let me think about time as being the fourth dimension. Then I have a movie of three-dimensional pictures, which is a four-dimensional picture. And that's how I would like to think about four-dimensional um, geometry. Four-dimensional geometry is a movie of three-dimensional geometry. I could do that in any dimension. So here, my first example to get us going is a two-dimensional movie, which means I'm describing a three-dimensional object. So think of it like slicing from -1 to 1, and at one point you hit zero, through zero, so you have a movie going from -1 time to 1, and in each step you slice, in this case, a ball, and you look, a ball in the cube, and you look at the corresponding slices. It's kind of a funny picture. So if you have the ball in the cube, so this picture, and you slice it successively from here to here with a hyperplane from -1 to 1. So what do you see? Well, at the first step, you just hit the full cube, right? You slice the cube. So actually the green background here is not really the green background, that is the cube. So this thing here is already the cube. Right? As soon as you hit the picture, you slice the cube. That's why it's always green in the background. However, for the sphere, it's slightly different. The first slice of the sphere, as you can see here, it's roughly here. You just slice a teeny weeny bit of the sphere, and then it gets successively bigger until you hit the middle, which is kind of the middle slice, where it is the biggest, and then it gets smaller again until the very end, where it's again more like a point. So this is a movie of slicing a sphere, right? So I slice it, slicing a sphere in a ball, in a cube. So the picture I have in mind, the ball in the box. I'm slicing a ball in the box. I always see the box because the box is just a box. If I slice it with a hyperplane, I always see the box. But the ball gets successively bigger and bigger from a little bit of a point, gets bigger, bigger, and bigger and bigger until it hits its full radius. It's a perfect picture. It's a perfect two-dimensional picture, which we have seen before here. So this one, you see it in the middle, and then it gets smaller and smaller and smaller again. If you do the same for dimension 4, you get this two-dimensional movie of a two-dimensional picture. So I said before, I could run a movie of a three-dimensional picture. That's what's running in our heads, but that's still a bit too hard to illustrate for me. So instead, what I'm doing is I'm replacing two dimensions by time. I have a horizontal dimension and I have a vertical time dimension, and I run this two-dimensional movie of two-dimensional pictures, which does the job in this case. So I have again the same setup from -1 to 1, from -1 to 1, and I run through the movie in horizontal or vertical dimension, and it looks exactly the same. So as soon as you hit the cube, so as soon as you hit the outside cube, the cube is there. There's nothing you can do. So it's always kind of filled green. And the ball will come out successively in a little bit of bigger slices the further you go to the point 0, 0 in time. So 0, 0 in time is the big slice here in the middle, and otherwise it kind of goes a little bit smaller towards the sides. So this is really nice. As I said, well known in low dimensional topology. It shocked me a little bit that it is actually so easy to think about higher dimensions. Just a movie of lower dimensions. Works pretty well. Of course, it doesn't really work for dimension 512, but for dimension 4 or 5 is actually pretty good. Movie of lower dimensions. Anyway, and the point is we wanted to answer this question. Just remember the volume of the ball in the box, the ratios, and this picture actually tells us that the ratio should go to 0. Why? Because in some sense, hypercubes have too many corners. So you can kind of see it in this picture already. In the corners of those slices, there's basically no ball at all, right? The ball is basically not there. And the further you go into the middle, well, it kind of works. It fills out more and more space. But in the corners, the ball is basically not existing. Here it's even worse. So in the corners, there's basically no ball, right? So, but the problem now in higher dimensions is that the cube, the hypercube, has quite a lot of corners in contrast to faces. So an n cube has 2 to the n corners. That's quite a lot. And kind of all of the volume of the cube is in the corners in some sense, while the volume of the sphere is in the middle. But there's kind of only one middle and a lot of corners. So what I would guess here is from this picture, you could make the guess that actually this ratio of volumes goes to 0, which is kind of already surprising. It gets even better, but this is already kind of surprising. I said in the beginning, what I would like to think of is having a ball that fits perfectly into a box. And I would like to think of how many space is left in the box. Right? I'm not throwing a pea in a box. I'm putting a ball that fits perfectly into the box. And I'm asking for what it remains. Turns out, and this is my conjecture on this slide, that I'm conjecturing in higher dimensions, what remains is basically everything because this ratio goes to 0. So in higher dimensions, this picture of a pea in the box is much more appropriate than the one of a ball in the box, which is always the curse of dimensionality, because it kind of doesn't want to make sense in my brain at least. But it should come out of this analysis that, or this idea that there are just too many corners in higher dimensions, right? How could we prove that? So at this point, this would be my conjecture because of those pictures. How could we prove that? Well, the volume of my cube with side length 2, that's easy. It's 2 to the n. So that grows pretty fast. As I said, there are too many corners, so it grows pretty fast. So we need a formula basically for the volume of the ball in n dimensions. You all know the formulas for volumes of balls in low dimensions, like the area of a circle, right? We learned them too early in some sense. So you learned very early the area of the circle. And then it took me a while to understand that there should be some kind of master formula that spits out the volume of spheres for any dimension instead of just having it analyzed case by case. And yes, there is a master formula, and I would like to discuss it now. So the master formula has an input n, the dimension, and it spits out the volume of the corresponding sphere, this ball in that dimension. So the master formula. And before I show you the master formula, so let me try to analyze what's going on. So I will kind of spoil the story now. So I told you in the very beginning, my setup was a ball in a box. My ball had radius 1. My box had radius, whatever you want to call it, side length 2. So in any dimension, this was true. The ball perfectly fits into a box of side length 2. What about higher dimensions? What about the converse? So now I fix a box of side length 1, and I would like to fit it into a, so here side length 1. I would like to fit it, or here the same. I like to fit it perfectly into a ball. My first naive guess would be, again, for any dimension there should be a certain ball that just fits the square or the cube, but it is actually not true. So the radius of the fitting ball depends on n, and it's kind of what's will be going on with the formula in the end on the next slide. So the formula for the radius, so here it's square root of 2 over 2, here it's square root of 3 over 2. It's actually square root of n over 2. So the radius of the outside ball that fits the cube goes to infinity, while I still fit the same cube of the same side length. That's kind of weird. Again, curse of the dimensionality. This is already kind of weird. So the radius, I said again, the radius of the fitting ball goes to infinity as the dimension grow, in contrast to the radius of the fitting cube, which is always 2. And if you think about it a little bit, what could this imply? Okay, so let's have a look at the formula now. The curse of dimensionality. So the volume of the sphere is actually given by the formula here that I put here. Don't look too close. It's not so bad. So there is a term which I have in green, which basically is a gamma function involved. Whatever, there's an even odd issue involved. Whatever, doesn't really matter. This green thing basically behaves like 1 over n factorial. So it basically drops drastically, 1 over n factorial. And the rest just can't keep up with it. So the rest is some powers of pi, depending on n and for the radius. In particular, for fixed radius 1, there's a pi to the something, and you divide by n factorial, that goes to 0 before you blink with your eyes. So in the blink of an eye, this is 0. So this is a plot of the dimension versus the volume of the ball. It kind of tends to peak a little bit, and then it drops, and it's gone, and it is really gone. Shocking theorem, the volume of the unit ball goes to 0 as n goes to infinity. Again, curse of dimensionality. It doesn't quite want to make sense in my head. The volume of the unit ball goes to 0. That's weird, right? Hyperballs do not exist in some sense. The volume goes to 0. While I said again, the volume of the unit cube still stays 1. Right? That's weird. That's just weird, right? The ball vanishes and the cube is still what it is. This is really, really, really surprising in my opinion. So this is just crazy. Okay, I say it again because it's so crazy. The volume of the unit ball just goes to 0 as n grows. Weird. Really weird. But simple mathematics. So to prove this formula actually does require some tensor calculus, for example, which is beyond me, but it's not so bad. So I think the proof is on Wikipedia, linked in the description. So it's not really so bad. In the end, it's not hard mathematics, but it's still a super surprising statement. Like, our brains just can't comprehend higher dimensions, or at least my brain can't. So I think this is really surprising. Turns out, and this is kind of before I wrap up, this is my the last thing I want to say. The peak is roughly around 5. So here at n equals 5, there's a peak of the volume. So as I said, this is volume versus dimension. So it does a little bit like this, and then it goes away because you have n factorial there, and it peaks around n equals 5. So what is actually so strange about n equals 5? Why is 5 dimensions so interesting? That took me a while to understand, and it's very nicely explained in the paper I mentioned that this talk is based on, linked in the description. And the answer is nothing is special about 5. So dimension 5 is not special at all. So why dimension 5? Well, it's just a fluke. In what sense? Well, let's have a look at the formula again. So here's the formula. Again, ignore the details. This is basically 1 over n. This will kill everything. The r is 1, so we can ignore the r. And then there's a pi to some power. And kind of the whole race of where the peak of this volume function is determined by the race between pi and n factorial. Or strictly speaking, there's an n over 2 factorial. Anyway, it doesn't matter. So this race will determine everything. In other words, the 5 is as special as pi in some sense, because it only depends on the value of pi. The only dependency is, as I said again, the value of pi for the corresponding peak. So here upstairs, for example, I plotted the peak, or the same function, volume versus dimension, for my favorite value of pi. Pi equals 8, of course. Who doesn't like 8? Pi is 8, of course it is. Anyway, and then it peaks around 15-ish. So there's really nothing special about 5. It's just the volume of the sphere peaks in dimension 5 just because pi is what it is, and it's kind of built into the formula. That's all. So 5 is not really special here. What is really going on, what is really important as a takeaway message, is not that it peaks and then goes down. That might be a little bit surprising, but the really kind of crucial thing that kind of is completely contradicting our perception of higher dimensions, whatever that means, is that the ball vanishes, right? The unit ball with a fixed radius vanishes in higher dimensions. So let me wrap up. So I started with this question of I want to put a ball in a box, and I want to kind of measure the differences between their sizes, basically. And it turns out that this is already a little bit surprising in the sense that the difference goes to zero. So the hypercube, in this case with side length 2, just grows to infinity in volume because it's 2 to the n, and the sphere just can't keep up. In some sense, the hypercube has too many corners. Okay, already very surprising. Um, as I said, in higher dimensions, it's really more like instead of putting a ball that fits perfectly in a box, it's really more like throwing a pea in a box. Right? The hyperball basically isn't there anymore. Okay, and then I turned it around and I asked for, maybe I don't want to fit a ball in a box. Maybe I want to fit a box in a ball. And it turns out something crucial happens, which explains everything basically, namely the unit hypercube, so side length 1, volume 1, fits into a sphere of growing radius, right? Fits perfectly into a sphere of growing radius. And since we measure volume in terms of hypercubes, by definition, kind of it is expected that this formula of the sphere needs to go to zero. And that's exactly what it does. By the way, you can also do this in different norms if you want. If you want to have a different underlying measuring system for volumes instead of the cube, linked in the description, you can use LP norms and you get different results. But in this case, it's really this phenomena that a ball in a box, a ball of radius 1 always fits in the box of side length 2. But a box in a ball, a box of side length 1 fits into a ball of bigger radius. And that kind of kills everything, or just explains everything. Then the volume of the ball needs to go to zero as n goes to infinity, which is this curse of dimensionality again. We can't just, our brain just doesn't want to understand what's going on, but it's not so hard in mathematics. In any case, I hope you enjoyed the video. I hope you don't get too fooled by the curse of dimensionality, and I also hope to see you next time.